This presentation is about some important special purpose registers inside our processors. But we'll start off first of all with a wee bit of a recap of some binary things we need to know. We need to know how to add binary numbers together, and there are a small number of binary addition rules. The first three are very simple. 0 plus 0 is 0, 0 plus 1 is 1. But when we've got 1 plus 1, we would answer that as 2, but in binary we represent that as 1, 0. Or 1 plus 1 plus 1 equals 3 for us in denary. In binary, we would represent that as 1, 1. Remember those rules for the next slide. We can then add bigger numbers, groups of bytes, or larger numbers again, by adding together pairs of numbers starting at the right hand side. 0 plus 1 is 1, 1 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0, 1 plus 0, 0 plus 1, 0 plus 0. Very simple. We'll have a carry in this one because 0 plus 0 equals 0, but 1 plus 1 gives us that 1, 0. 1 plus 1 is 2, or 1, 0 in binary. So we put down the 0 and carry a 1 to the next column. The next column now has a 1, a 0 and a 0, so the answer there is 1. 1 plus 1 equals 1, 0, so we put down the 0 and carry the 1 and get a 1 in the next column. And for the third time, 1 plus 1 is 1, 0, show me the 0, carry the 1 and a 0 at the left there. Final one is more complicated again. We've got lots of 1s to add together. So 0 plus 1 is 1, 1 plus 1 is 0, carry a 1, and now we have 3 1s to add together. We don't put 3, and instead we say 1 plus 1 plus 1 is 1, 1. So we put down a 1 and carry a 1. And the next column, 1 plus 1 plus 0 is 0, carry 1. 1 plus 0 plus 0 is 1. 1 plus 1, 0, carry 1, 1 and 0. And I was careful to make sure I only ever finish up with 8 bits. I've not added big numbers where I would struggle to represent those using 8 bits, which we'll see in a moment. In an 8-bit binary number, the leftmost bit is referred to as the most significant bit. That's like the biggest column. The rightmost bit, the units, is the least significant bit, and we'll use that term later. And final bit of revision, just a reminder of how the range of 2's complements. We use positive and negative numbers in 2's complement representation. When you see a 0 in the most significant bit, we know those are positive numbers. When we see a 1 in the most significant bit, we know that those are negative numbers. Again, remember that for later. With that wee bit of revision out of the way, we can look at these registers. Registers are temporary storage locations inside the processor. There are some general purpose registers and some special purpose ones. These ones are to help us work with different types of arithmetic. So they're called flag registers because they can flag up or signify some sort of state of the process, the status of something inside the processor, the status of a calculation. A register can be set to 1 if it's true or 0 if it's false. And we need to know about 4 important ones in this presentation: whether there's a carry, whether the result is 0, if there's a sign to be negative or positive, and if an overflow error has occurred. Carry, as we saw in the worked examples, is when you add 2 numbers together and have a carry into the next column. This is when the carry flag would be set when there is a carry out from the 8th bit, the most significant bit. If you do a calculation and you get 0 as an answer, then the 0 flag would be set to 1. If you do a calculation and you have a negative result, that would be set to 1. If it was a positive result, it would be set to 0. And finally, if you add together 2 numbers and the processor can't cope with the size of those numbers, then the overflow flag can be set. Simple wee example here where there's no carry out at the end. We've got calculations just like we've done previously, but the 8 bits can store the result of that with no problems. There is no carry out from the final calculation. 0 plus 1 with no carry equals 1. There is no carry carried out to the 9th column, so the carry flag is set to 0. In this example, we've got bigger numbers. This is the 128 column because these are unsigned numbers. When we add together those larger numbers, we get a 0 and we carry out the 1 to the 9th column. So in this case, the carry flag would be set. And that's a way in which the processor can actually represent larger numbers, an 8-bit processor, than just 1 to 255 if it uses the carry flag too. An overflow error is when the processor can't deal with the result of a calculation. If we add together two negative numbers and gets a positive result, something has gone wrong. If we add together two positive numbers, get a negative result, equally something has gone wrong. We can add together negative and positive numbers. We can use 2's complement representation to do binary arithmetic, and that works. There's no problem with these calculations here. We can store -1 or +5 as results. Those calculations work. Or with 8 bits, no problems with those calculations there, though they're all within the range of what 8 bits can store and calculate. So an overflow occurs if we've got two 2's complement numbers and their most significant bit are the same, then the most significant bit of the answer is different. So in this first case, adding together two negative numbers, that red 0 there indicates a positive result. That's an overflow. In this example here, there's no overflow because we've got a negative number, and we get a negative result. That's perfectly fine. But in the first example, if you get a negative number, and a positive result, then that's an overflow. So the overflow flag would be set for this situation on the left. A couple of examples just to finish off, where we've got binary numbers along the top. You perform the binary calculations. 1 plus 1 is 0, carry the 1. 1 plus 1 plus the carry gives us a 1 here. You can see the carries are underneath. So you can follow that through. At the end, we've got 0 plus 0 plus a carry of 1 gives me 1. So there is no carry out at the end. So the carry flag is not set. We do have a problem though, because these are positive numbers. The zeros tell me there's two positive numbers added together, and in my result, my 8th bit is showing me a negative number. That means there has been an overflow. We can add together 127 and 7 and store 134 using 8-bit 2's complement. So that situation there is an overflow, and the sign flag would both be set. And in my second example here, look at the numbers along the top. We've got a negative and a positive. We add those together. This is -24 and 24, so we expect the answer to be 0. When we add these values together, we do get a value of 0, so the 0 flag would be set. There is also a carry out from the most significant bit, so that would be set to 1 as well. But there's no overflow, there's no sign, so that's when 0 and carry could be used. In summary, the overflow flag is only used for 2's complement addition, and it's when we see it when two negative numbers produce a positive result, or two positive numbers produce a negative result. Carry flag can be used with 2's complement or unsigned integers, and it's when we get a carry out from the most significant bit. 0 flag when a calculation produces a result of 0, and a sign bit when the overall answer has got a 1 in the most significant bit. It's a copy of the most significant bit. There's questions on OneNote to accompany this presentation.